All right, and here's where we start to mix and match probabilities with these combinations. So first, let's figure out how many different 5-card hands can you have in a poker hand, right? So you know that there's 52 cards in the deck, and you're looking to choose just 5 of them. And it doesn't matter which card you're dealt, first, second, third, or fourth, or fifth. All that matters is that you get 5 cards. And so that is a combination. You're looking to do 52 choose 5, which gives us 52 factorial over 5 factorial times 52 minus 5 factorial. Simplify the parentheses first. So that's going to give us 47 factorial. 47, again, is the larger of the two numbers. And so we come up here and expand the 52 until we get to 47. Looking ahead, we know that 52 factorial, once you get to the 47 factorial, that gives you times 47 times 46 times 45, so on, which is already wrapped up in the denominator here. So we're going to be left with 5 times 4 times 3 times 2 times 1. From the 5 factorial, you have a 47 factorial over here. Those cancel each other out really quick. And then we look to see what else we can cancel. So I see 4 times 3 times 2, which is going to give us 24. And 24, when you divide that out of 48, leaves you with a 2 in the top. And then the 5 goes into 50 with a 10 left over. So altogether, you get 52 times 51 times 10 times 49 times 2 for a grand total of 259,860. I misspoke. So there's 2,598,960 different 5-card hands that you can have in poker. That's a lot of cards, or a lot of different ways of putting together those cards. So next we want to figure out the probability of being dealt all hearts. So you get a flush. And so if you've ever looked at the kind of extra cards that you get in a deck of cards, there's one that may or may not tell you the different probabilities of hands. This is how you rank those. So 2 of a pair is more common than 3 of a pair, so 3 of a pair outweighs a 2 of a pair, and so on. So if we want to figure out the probability that we get all hearts, well, we need to first figure out all different combinations of getting just the hearts. So there's 13 hearts in your deck, and you're looking for all different combinations of 5 of those over the thing that we just calculated, all possible hands in poker. All right, so we already calculated the top number, or sorry, the bottom number, 2598960. How about off to the side, we calculate what 13 choose 5 is, just to see how many different hands will be all hearts. So again, that's 13 factorial over 5 factorial, 13 minus 5 factorial, which gives us 13 factorial over 5 factorial times 8 factorial, which gives us 13 times 12 times 11 times 10 times 9 times 8 factorial, all over 5 times 4 times 3 times 2 times 1 from the 5 factorial with an 8 factorial out here. Those cancel out nice and quick. And again, we just start looking for things to cancel. So 5 times 2 gives us 10, 4 times 3 gives us 12. So that gives us 13 times 11 times 9. Right, so it's going to give us 1,287 different 5-card hands that are all hearts. And if we want to figure out this probability, we take the number that are all hearts divided by the total number of hands. So that's going to give us roughly 0.0005, which is a very low number, which is why if you get a flush, you'll beat most other hands in poker. Now, let's suppose that you have 11 letters, where you're given 1 M, 4 I's, 4 S's, and 2 P's. And you're looking at all the different permutations of this. So we're going to look at all the different distinguished permutations. First, before we even move on to the next part. So the distinguished permutations, you have 11 numbers total, 11 letters total. You have 1 M, 4 I's, 4 S's, and 2 P's. And if we expand that out, we have 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. 1 factorial is 1, so I'm just going to leave it off to the side. We're going to use one of the 4 factorials to write out. The other 4 factorial goes over here that we can cancel. Then we have 2 times 1. So these cancel. You have 4 times 2, which gives you 8. Then you have 3 times 2, which gives you 6. So altogether, the number of distinguished permutations of those 11 letters with multiple repeats, it's going to be 11 times 10 times 9 times 7 times 5, which gives you 34650. And so we're asked, what is the probability that you randomly arrange the letters to spell the word Mississippi? So the probability that we spell Mississippi out of those letters, well, there's only one way to spell it once we essentially took all the all the permutations of it that did spell it and considered it as one. So there's only one out of all possible distinguished permutations. All right, so this is going to be roughly 0.00003. Right, and so there's a very slim possibility that if you just randomly selected those 11 letters, that you'll actually end up spelling the word Mississippi. And so this table down here tells us how we count things. Use this while you're working on worksheets or studying for the exam. The first thing that we saw in section 1 was the fundamental counting principle, which said that if one event can occur in m ways and a second event can occur in n ways, then the total number of events that the two events can happen is going to be m times n, which is that formula. And then in this section, we learned about permutations, where again, permutations, order matters. It really matters which one you choose first, and then second, and third, and so on. And so that gives us n factorial. Now, if you're only looking to take, say, r many of those objects out of the n many possible ones, that leads us to this calculation of a permutation of r objects from n objects. And like we saw in this last example when we were dealing with the word Mississippi and how it breaks up into letters and certain letters repeating, we don't want to count the same word twice if we just switch which S we're considering to be the first one, let's say. So that leads to this distinguished permutation. And this is what you'll get when you have, say, repeated things that you want to consider them to actually be the same, because they are, honest to goodness, the same thing. And we finished with combinations where order does not matter, right? And if order doesn't matter, then the number of ways of choosing r things from n things is going to be n factorial over n minus r factorial times r factorial. And again, always take care of the stuff in the parentheses first. Expand out your factorial in the top of the fraction until you can cancel out the larger of the two factorials in the bottom. Expand the remaining factorial and just start canceling things out. It'll help with plugging things into the calculator.